Hey everyone, welcome to the next video for Chapter 7. So in this video we're going to do an example, which if you look at the title above, you should kind of see what's going on here. We're doing an example of a two-tank problem, which, tank problems in general are rough. But this one's, we're going to go through it and see how this gives rise to a system of ODEs that we could then try to solve. Once we get to the point of learning how to solve these equations, we can try to solve this by those methods. All right, let's go ahead and start talking about the two-tank problem. So as you can assume by this problem, we're going to be dealing with two tanks of water that have varying amounts of salt in them, water flowing in and out of the different tanks, and we want to analyze what happens to the salt concentration in the two tanks over time. So I'm just going to go ahead and write up the whole problem for you now, and then we'll start talking about it. All right, so here's a lot of words, and it's going to sort of set up a word problem to model two tanks. The idea of the problem is to set up ODEs that model this system. It's going to end up being an ODE system here because we have two dependent variables. We have the amount of salt in both tank 1 and tank 2 giving us two functions to deal with. So there's two tanks of water. Tank 1 contains 100 gallons of water and 20 pounds of salt, while tank 2 contains 200 gallons of water and no salt initially. Water with a salt concentration of 1 pound per gallon flows into tank 1 at a rate of 3 gallons per minute. Water is removed from tank 1 at a rate of 4 gallons per minute, 2 gallons of which are pulled into tank 2, while the other 2 are just removed from the system. A recycle stream takes 1 gallon per minute back from tank 2 into tank 1, and a 1 gallon per minute flows into tank 2 normally. Both tanks are well mixed, so we have the normal assumption on the concentrations. So we can look and see, first of all, we can look and see do volumes remain constant? And the answer here, they do remain constant because for tank 1, you're putting in 3 gallons per minute plus 1 gallon per minute is 4. And you're taking out 4. And for tank 2, you're putting in 2 and you're removing 1 and 2. So both volumes are constant, which is good. So let's set up a picture and then start writing ODEs to model this situation. So I have X1 over here, and V1 is 100 gallons. I have X2 over here, and V2 is 200 gallons. I have an inflow stream that's 3 gallons per minute and 1 pound per gallon. I have a stream that's coming out of here and going into here, which is 2 gallons per minute. I have a removal stream that's also 2 gallons per minute. I have removal here at 1 gallon per minute, and a recycle here at 1 gallon per minute. Okay, so let's look at X1. So how does X1 change? Well, the rate of X1 change is going to be salt in minus salt out. So what is salt in? Well, salt in is 3 gallons per minute times 1 pound per gallon from the inflow stream, plus this other inflow stream. So the inflow streams for tank 1 are this one and this one here. And then we have an outflow stream for tank 1 of outflow and outflow, these two down here. So inflow is that plus 1 gallon per minute times X2 over 200, which is the concentration of the salt in the second tank, and then minus a total of 4 gallons per minute times X1 over 100 for the concentration in tank 1, because the two outflow streams do the same thing, so I can just put them together to get 4 gallons per minute. And similarly, I can think about tank 2. So X2 prime, the amount of change of salt in tank 2, is going to be the inflow stream, which is 2 gallons per minute times X1 over 100. And then outflow streams are minus 2 gallons per minute times X2 over 200, because I can put these two outstreams together because they're the same sort of thing. So now if I re-put all this together in sort of combined terms, I see that I get X1 prime equals 3 plus X2 over 200 minus X1 over 25, and X2 prime equals X1 over 50 minus X2 over 100. So that gives me a system of ODEs that I could try to solve. Now if I wanted to write this in matrix form so it looks nicer, then I get something that looks like this. X vector prime equals, what is my matrix? My matrix is going to have the x1 first, so 1 over 25. X2 is 1 over 200. X1 is 1 over 50. X2 is negative 1 over 100 times x1, x2, which is my vector x, plus the vector 3 times 3, 0. And this here is my ODE system for that tank problem given in matrix form. Now, we're not really going to see how to solve this until we get to the end of the chapter because this is a non-homogeneous problem because it's not just 0, there's a vector there. But eventually we'll see how to solve them. We'll see how to solve problems similar to this as we go on. All right, that was my point here. So we had tank problems before and they were annoying. Well, now we have 2 tank problems coming back and they are a little bit worse. But there won't be too many of these that you'll see. You'll see a couple little modeling ones like this, but nothing too complicated. This is probably the most complicated thing you'd see. All right, thanks for watching, and I'll see you next time. We're going to go into some of the theory behind linear systems of equations.